All right, everybody. So in this chapter, this part of the chapter, we're going to cover a little bit of a review of addition chemistry, and we're going to start talking about oxymercuration-demercuration and some other addition chemistry. So you'll need to go through this prior to lecture on Friday, and on Friday we'll have the inverted lecture where we're actually working problems covering this material in class. So the oxymercuration-demercuration procedure is actually a two-step procedure that's pretty interesting. The first step being the oxymercuration, where an alkene reacts with water in the presence of mercuric acetate. That's abbreviated as HgOAC in parentheses 2, where OAC is the acetate anion that is derived from acetic acid. And it turns out that mercury acetate is an electrophile. It will react with a carbon-carbon double bond. But interestingly enough, it doesn't generate a carbocation. And we'll see about that in just a moment. This is typically done in a mixture of THF and water. THF is needed to make everything soluble in the water to get the mercury in, and THF and water are miscible with one another. So it's a pretty good reaction mixture for this. And so in the first step, you have an alkene. You have mercury acetate, water, THF. You generate a oxymercuration product where a mercury atom and the oxygen from water as a hydroxide is actually added across the carbon-carbon double bond. We call this an organometallic species because it has a single metal carbon bond. And you get acetic acid in the process. And so you can see that we've added what looks like at least half of water and an electrophile. And so in all the other additions, the electrophile was a proton. Here it happens to be mercury. Well, in the next step, what we do in the demercuration step is we actually react this with sodium borohydride, which is a good reducing agent. And it reduces off the mercury and replaces it with a hydrogen. So really what we've done over this two-step process is actually add water across the carbon-carbon double bond. But in the process, we also ended up making mercury metal. Not particularly environmentally friendly, but nonetheless, this reaction works really well. And you get another molecule of acetate anion in this reaction. So it's a very simple procedure. The yield in this reaction is actually usually quite high. Quite frequently, it's just simply quantitative, 100% yield. The reaction's over quite quickly. Can be done within just a few minutes. The cool thing about it is that the mercury metal, which you all know is a silvery liquid at room temperature, looks like it's raining out of solution when you actually do this reaction. So it looks like a little fine mist of mercury rain is falling out of the solution. I'm actually going to do this particular reaction in class on Friday as a demonstration to show you how this works. And so it's got some cool color changes in it that I want you all to be familiar with. So, for example, let's look at these reactions. So 1-hexene reacts with mercury acetate and then followed by sodium borohydride in the presence of base. The base is just there for your information, not to put the OH on the alkene. It's there to keep the sodium borohydride from reacting with the water that it's dissolved in. So sodium borohydride is actually quite stable in basic water, and so you just add a little bit of sodium hydroxide to it. But nonetheless, we're going to react 1-hexene under the oxymercuration-demercuration procedure, and you end up with 2-hexenol, or hexanol, not hexenol, hexanol. That should be an A. I don't know why the book did that. But 96% yield, quite good. And as you can see, it's a Markovnikov alcohol, as one would expect. You can take mercury acetate here and sodium borohydride in the oxymercuration-demercuration sequence. Here with 1-methylcyclopentene, and again, get the Markovnikov alcohol in very good yield. It's essentially quantitative. Here we have the situation where we have 3,3-dimethyl-1-butene. We're going to do this reaction. Now, the interesting thing about this is it works very well. You get greater than 90% yield. You get the Markovnikov product, but there's no rearrangement. So if you were to do this reaction in the presence of sulfuric acid and water, you would actually get a rearrangement. Now, what I want you to do before you come to class on Friday is work out the mechanism with the rearrangement for this reaction. Okay, this alkene that we have here, but instead of doing the oxymercuration-demercuration sequence, just use sulfuric acid and water. And put this on a note card, and I will give you a bonus point on your inverted lecture. So if you miss any points on your inverted lecture, you can get a bonus point for doing this. But you have to come to class with this ready before we actually hand out the inverted lecture. So get a 3x5 note card, put your name on it, work that problem out on the other side, and bring it to class. And I can give you a bonus point. Okay? Now the reason that the oxymercuration-demercuration sequence does not result in rearrangements is because you never have a true carbocation that's formed in the reaction. So, for example, if you take mercury acetate and you place it in water, it actually forms an equilibrium between mercury cation and acetate anion. So you have this mercury plus that's bound to one acetate, and then you also have a free acetate in solution. Now this is an equilibrium reaction, but it turns out that the mercury that's positively charged is a pretty good electrophile, and it will react with the alkene, where the alkene carbon-carbon double bond reacts with the mercury, but also the mercury has lone pairs of electrons around it that come back and forms this three-membered ring called a mercurinium ion. It's really kind of a complex with the alkene. And what you can see is that the mercury still bears the formal positive charge. And so that mercurinium ion then undergoes attack by water and results in the Markovnikov alcohol. Now I've worked out on a piece of paper the mechanism for the reaction of mercury acetate and water and with this particular alkene to show you that you never have a true carbocation and how the water attacks the most substituted carbon. So the slideshow will stop here in just a second. You'll see the video for that being worked out on a sheet of paper, and it'll show you the mechanism there. Okay, so we just talked about the oxymercuration-demercuration sequence on the slides, and I want to go over the mechanism real quick at this point. So if you take mercury acetate, and OAC is just an abbreviation for acetate, so it's mercury 2 acetate, and you place it in water, you actually get mercury cation, okay, plus acetate anion in solution. And it turns out that the mercury cation will react with an alkene. So the alkene that we used previously was this alkene, and it will react with the mercury acetate that's formed to give you the mercurinium ion. So I'm going to exaggerate the bonds just a little bit here. So one bond to the mercury is actually larger than the other, and so the mercury still bears a positive charge, and you still have acetate around. And so this bond being longer than this bond means that this bond is weaker, and so now when water comes in and attacks to form the alcohol, it's going to attack the most substituted carbon, which seems counterintuitive, but the reason it does it is because this is the weakest bond. And so those electrons then go onto the mercury atom. You end up generating the OH here. You put the mercury on that particular atom, and of course acetic acid, now HOAC, because the other hydrogen and water had to go somewhere, and so the acetic or the acetate, excuse me, abstracts that proton from the protonated alcohol. And so this is how you end up with a Markovnikov alcohol through the uh, oxymercuration-demercuration sequence. But what I wanted to show you was the mechanism for the oxymercuration sequence. And so you can see why we call it oxymercuration. You have an oxygen and a mercury that's added across the carbon-carbon double bond. And so this looks like an alcohol. We now have what we call an organometallic species because we have a metal carbon bond. And in the second step, the sodium borohydride actually comes in and displaces the mercury, and you end up generating mercury metal, mercury in the zero oxidation state, which precipitates out. So I'll just draw a down arrow. You end up generating another molecule of acetic acid, and you end up generating the Markovnikov alcohol. And the cool thing about this is that there's no rearrangement because there's never a carbocation. Had we done this reaction just in the presence of sulfuric acid and water, we would have actually got a rearrangement to occur because the secondary carbocation that we would have generated would have rearranged to a tertiary. So that's the mechanism in general for the oxymercuration-demercuration sequence. And you can now continue on with the slideshow for our inverted lecture on Friday. Okay, so now suppose we have the alkene shown here. This is known as isobutylene or 2-methylpropene. If we take water and sulfuric acid in catalytic amounts, we're going to add water across the double bond, and we're going to end up with 100% of this Markovnikov alcohol. Now suppose, however, that we don't want this alcohol. We actually want the anti-Markovnikov alcohol, where the OH is actually on the least substituted carbon and the hydrogen is on the most substituted carbon. Markovnikov's rule doesn't allow for this, and so we need another set of reagents that allow us to do this chemistry. And so that's where hydroboration oxidation comes in. And you'll remember from the other day in class, I talked about the fact that we have these two sets of reagents that will add water across a carbon-carbon double bond. And we had talked about sulfuric acid and water, and we had talked about the hydroboration oxidation. And it didn't quite look obvious as to why we needed these different sets of tools to make an alcohol. And it turns out that the hydroboration oxidation sequence allows us to convert an alkene into an alcohol, but it allows us to convert that alkene into an anti-Markovnikov alcohol. That's very, very important. So if you have a carbon-carbon double bond and you react it with BH3, so this is borane, it's known as borane. You'll notice that boron doesn't have an octet of electrons around it, so it's a good electrophile. Borane comes in a variety of different reagent types, but they all behave as BH3. So for example, you can have BH3.THF, BH3.DMS, BH3.pyridine, you can have B2H6. All of those reagents actually behave as if they are BH3. And so what happens is the alkene will react with the borane to give an alkyl borane, where we now have a carbon boron bond. And it turns out, they're not showing it here, but this resulting borane will actually continue to react with alkene until all the boron hydrogen bonds are gone. So you only really need, for every mole of borane, you need 3 moles of alkene. So it's a 3-to-1 ratio for this, although they're showing this here as a 1-to-1 ratio. Once you have this, you'll notice you've put a carbon-hydrogen bond on, and you now have a carbon-boron bond. And you can react this with basic hydrogen peroxide, and you can oxidize off the boron and actually end up putting an alcohol. And so during these 2 steps, we've actually added water across the carbon-carbon double bond, but we've done it in such a manner as to generate an anti-Markovnikov alcohol. So as I mentioned, there are several different types of borane reagents. The common one that we're going to focus on, well, actually there are 2. Borane comes actually as a dimer, B2H6, and it's highly reactive, and it will decompose into BH3 quite readily, and it will react with any type of Lewis base. So for example, you could take borane, which is a Lewis acid because it'll accept a pair of electrons, and tetrahydrofuran, which is our cyclic ether here, has lone pairs on the oxygen. It'll function as a Lewis base, and you can actually form what's called a BH3 dot THF. This dot means that you formed a complex. And so in solution, the borane BH3.THF is actually in equilibrium between BH3 and BH3.THF. And so it behaves like it's BH3, but it's a lot more stable to work with. So it's not a gas. BH3.THF is actually a liquid that you can handle quite easily. So it turns out that the mechanism for this is a concerted reaction where the hydrogen and the boron bonds are all being formed at the same time. You can see that the two arrows are being used here, so we're moving a total of 4 electrons. So the pi bond comes out and reacts with the boron at the same time that the boron-hydrogen bond reacts with the other carbon. And so you're delivering the hydrogen and the boron from the same face, and so you end up with what's called syn addition. So the hydrogen and the boron are actually being delivered from the same face of the alkene. Okay, and I already talked a little bit about this, so we'll skip that for all practical purposes. And the borane being an electrophile, it's going to follow, the boron is going to follow Markovnikov's rule, and it's going to get bound to the least substituted carbon. Okay, just like a proton does. So when these electrons come out and react with the boron's going to be on the least substituted carbon, and the hydrogen from the borane is going to go onto the most substituted carbon. And so that's how you end up with the hydrogen on the most substituted carbon. And remember now that the boron can be oxidized off with hydrogen peroxide. And so when we remove the boron and replace it with an OH, it looks like we've added water across the carbon-carbon double bond in an anti-Markovnikov fashion. And the only way that we were able to achieve that is by tricking Mother Nature, if you will, by using this boron as our electrophile instead of a proton. So it all has to do with transition state stability. This is the more stable transition state because as the reaction occurs, you're building up a slight positive charge on one of these carbons. So it can either be the most substituted carbon or the least substituted carbon. And we know that the more groups we have around a carbon that is positively charged, the more stable it is. And so this is the more stable transition state. And that's why you end up with this as the only product out of that particular reaction. And so the boron is then oxidized off using basic hydrogen peroxide. And it turns out, interestingly enough, that occurs with retention of configuration. And so the hydrogen atom and the boron are going to be on the be delivered syn, so it's syn addition. And then when we replace the boron with hydroxide, it too retains that configuration. So water is actually being added in a syn fashion using the hydroboration oxidation step, or sequence, excuse me. So we'll work some more examples in class on Friday. Don't forget the note card thing that I talked about. You need to do that in before you come to class. That's going to be due at the very beginning of class, and I can give you up to a bonus point that could be used on your inverted lecture. So if you miss a point here or there, you can get a free point back. So see you all on Friday. What the heck? Nothing for you to worry about.